Hello, calculus students. Welcome to another online lesson. Today we are continuing our discussion of binomial expansions. Last class we looked at Pascal's triangle, and this class we are looking at what's known as the binomial theorem. And we're going to use that to expand binomials and find specific terms. So the binomial theorem allows you to calculate any term of binomial expansion, and it follows this pattern. It's in your formula packet, and it looks like this. So you've got some a term and some b term to the power of n. And we can see that we talked about with Pascal's triangle, you start off with your a term to the n power and then to the n minus 1, and then it just keeps getting lower and lower until you eventually have no more a terms at all, or a to the 0 power. The b term, on the other hand, we start off with no b terms, and then we have 1, and then it keeps increasing until we have b to the n, which was, again, our original exponent there. The coefficient we get using this choose notation that we saw earlier in the year, n again being our exponent, and then we simply choose the whichever term we're at, minus 1. So the first one we have n choose 0 essentially, which just becomes 1, and then we have n choose 1, and so on and so forth. So that's what's happening there. It's vast, and I'll be completely honest, I don't love this formula. I don't use it, but I do use this part of it. And again, this is exactly how it appears in your formula packet, so I just jump straight to this guy right here. So what does all this mean? Well, n is the power of your original binomial. R is the power of the b value that you're looking for. Power of the a value is n minus r. And then you've got this a and this b. And all together, this reminds me exactly of the binomial distribution formula. And that's why I teach it right after that unit, because we have, your big exponent, the number of things, or the number of trials, the number of things you want, your probability of success, your probability of failure, all that sort of stuff. Very, very similar. The b and the a are technically flip-flop, but I think it's, we're comfortable with something like that. Now, what does that formula find you? Well, you can see that I've got it here. I call it the general term, or whichever term you're looking for plus 1, this will get it for you. But oftentimes, I'm not even concerned whether it's the third, fourth term, but if it is, I need to add a 1 to that. And that's what this does for us. So the best way to sort of check this out is actually look at some examples. And this first question says, find the term containing x to the third power in the expansion of 2 minus 3x to the 8th power. Now, once again, what we're not going to do is FOIL. We could do it. I would probably likely make a mistake here or there. I would definitely need a calculator to do it. And it would take some time. The idea is that we can use our formula to get through this a little bit faster. Now, we don't need to expand every term. They're looking for one specific term containing x to the third power. So if we write our formula out, we've got n, choose r, we have a to the n minus r, and we have b to the r power. Well, let's think about what we want. First and foremost, we can label a few things. A is obvious. A is 2. And b is pretty obvious as well. B is 3x. Or I'm sorry, negative 3x, right? We have our two terms here, our a and our b does have a negative rather than a positive, so I've put that in there with it. That way we can assume normally that everything else is positive. What we still need is n, and n's pretty obvious as well. N is going to be 8. So the only thing we're actually looking for is r. That's the only thing we have questions about. I want you to take a moment and look at this problem and see if you can figure out what r has to be. Now remember, a is going to be our 2. We know that a is 2, and we'll take that to some power. We're trying to get x to the third power. Which term has an x in it? Well, a does not. A is just a constant of 2. B is the only one that has a power, or that has an x to it. So whatever we raise b to, In that particular term, that's going to be the exponent of our x. What do we want to raise b to? We want to raise it so that we have an x to the third power. So r, as you can see here, has to be 3. If you didn't quite catch that, pause the video here. Take a look at it again. Rewind it. See if you can see why b has to be 3. Again, when we do our substitution here, and I'll write that off to the right here, we know that n is 8. Why? Because we had an exponent of 8. No problem. R, we weren't sure about. A, I'm going to use parentheses here to group that. We had a 2. And we take it to the n minus r. Well, that's 8 minus something. And again, we weren't quite sure what r was. And then we've got our second term, which is negative 3x. Again, that was obvious. In our binomial, you always have 2 terms, an a and a b. Our b was negative 3x. We still didn't know what r was, but we were trying to find a term that contained x to the third. Now, no matter what exponent I took this 2 to, it's not going to create any x's. I can take it to the 100th power, I can take it to the first power, the 0 power, whatever. No x's will appear. The only way I'm getting x's is by doing something with this term right here, the negative 3x. And since I want to have it to the third power, we can go back to this formula and see that r had to be 3. So then I'm plugging in those 3's there. So if you see that right away, this has become a very quick problem. We're just identifying some values very quickly and then throwing them in. Now, how do we actually do the math here? Well, I'm going to reach for my calculator. And the first bit of math that I needed was 8, choose 3. So I do 8 math. We go to our probability NCR. So 8, choose 3. And that was going to get multiplied by my a term, which was 2. And we're taking that to the power of 8 minus 3, or n minus r, which in this case is 5. And I'm multiplying that by our negative 3x. Well, I'm not going to put the x into the calculator, but I will put the negative 3 into the calculator. And that is all to the r power, which we said was 3. And then I can go ahead and hit enter. And so I get negative 48,384. And then, of course, the x we already figured out was going to be x cubed. So our final answer, after all that, is negative 48,384. And it's x to the third power. Now, this one actually asked for the term. Well, here's your term. Other times they might ask for just the coefficient of the term, in which case that's what I got straight off the calculator. All right. Example 2, consider the expansion of 3x squared minus 1 over x to the 9th power. First and foremost, part A, how many terms are there in this expansion? Well, we know that if we had, as we looked at last class, if we have something like a plus b to the 0, that ends up becoming 1. And if we have a plus b to the 1 power, that ends up becoming a plus b. So when we have a 0 power, we have 1 term. When we have a 1 power, we have 2 terms. If we square it, we get a trinomial, so 2 becomes 3. So our number of terms is always 1 more than our exponent. So we know that if this exponent is 9, we must have 10 terms. And again, from Pascal's triangle, we know there's always 1 more term than the value of the binomial's outer exponent, which is 9 in this case. So again, 10 terms in this expansion. So now let's go on to part 2. Part 2 said, what is the term with a constant? And let me back up, actually, make sure I read that correctly. Find the constant term in this expression. Constant term. So constant is the one that has no x's involved. Well, it's weird because they both have an x here, we see. We've got a 3x squared here. We have negative 1 over x. They both have an x, but at a certain point with a certain exponent, those x's will essentially cancel out. And we want to know which term that is. So we're going to use that formula again. We have n, choose r. We're taking our a term to the power of n minus r, and our b term to the power of r. As always, there's a few obvious things here. Our a is obviously 3x squared, a term, and then our b term once again is negative, and so our b is negative 1 over x, or if you want to call that negative x to the negative 1 power, that would work as well. And then what else do we need? We need n, which we know is going to be 9. And just like last time, r is the only one that we're concerned about. So we need to set up an equation that will allow us to figure out when our exponents essentially of x go away. We don't want to have any. We want to have our x's have a 0 exponent, so they have essentially canceled out. So what I'm going to do is I'm going to take the information we have so far and plug it into the formula. So I've got n choose r, and it's going to be 9, and I don't know what r is yet, so I'm going to put the r there. And then I am going to put my a value in, which is 3x squared, and I'm taking that to the n minus r power, which is 9 minus r, and then multiplying that by b, and b is negative x to the negative 1 power, I think is the easiest way to look at that. Again, negative exponent flips us, and we just have 1x. And then the r value is the thing that we don't know. Now, what is important to this? We need to get a constant. So I don't really care about my coefficients. So the 9 choose r doesn't affect me. Honestly, this 3 doesn't even affect me. The negative doesn't affect me. The only thing that I'm concerned about is when all these exponents of x right here end up becoming 0. And so we need to make it so that these guys become 0. So we essentially have an equation here already. Now 9 minus r, if you're already squaring something here, and then we take it to another power, what do we do with that? Well, we end up multiplying. So we're going to have 2 times 9 minus r. And that will be an exponent of with a base of x. So we essentially have x to the power of 2 times 9 minus r, but I'm not going to worry about the x right now. And then I have another exponent, which is negative 1 times r, also known as negative r, which will also have a power of x. And those x's that we have for both of these are getting multiplied together. And when we multiply the same base, what do we do with the exponents? We add them. So I'm taking these exponents that we have here, this guy which went with the a term, this guy which went with the b term, and I'm going to add them together so that they equal 0, because I want them to cancel out. I want to get a constant. I want to get rid of all my x's. So I distribute. I get 18 when I take 2 times 9. 2 times negative r is negative 2r. And then I have another negative r right here equals 0. So that gives me negative 3r, and I have the 18 here, equals 0. Subtract 18 from both sides. Negative 3r equals negative 18. Divide by negative 3, and r equals 6. Am I done with the problem? No, it said find the term. I still need to actually get this constant. So I'm going to go back now to my original setup. I need 9 choose 6, and then I have 3. I'm not going to worry about the x's. I know they cancel out, so I'm just going to take 3 to the 9 minus 6, and then I know that the other term is nothing but x's. The only thing I need to be concerned about is the negative that we had here, but it's going to be raised to an even exponent of 6, so that's going to go away as well. So it's just going to be 9 choose 6, and then 3 to the third power. Well, I already know 3 to the third power is 27, so I just need to do 9 choose 6 on my calculator. So 9 math choose 6 equals this times the 27 that I had for my constant, and my answer is 2,268. That would be the constant term in this equation. Again, what did I do on this problem? Well, we can recap it all for you right here. One last try. Okay. So we started off identifying what we knew already. We're using this formula, and we figured out what our A term was, our B term, our N, and it's the R that we didn't know. We set up what we knew in the problem. We took our exponents that we had, and we knew that specifically of the x's, and we knew that those exponents we wanted to see cancel out, so there'd be no more x's left. So we wrote this equation right here. We did our algebra to get r equals 6, plugged it back into the calculator to end up with our answer of 2,268. Ladies and gentlemen, that is the binomial expansion formula. There's other good examples on page 185 and 187. We looked at a couple. There's a lot of different variations, so if you're looking for more examples, you can check that out. And our homework is on page 186, number 2 through 5, and 7 through 9. We'll have a worksheet next class, and until next time.